First of all, I apologize. With the shorter classes, I used to begin every class with 15 minutes or so of going over the previous day's homework, and something's got to give somewhere. So sometimes you're going to hear me say, you got to hit me up during the flex. This is a nice one. Did you get the acceleration part? Okay, you just let this be a big 14, and away you go. Okay, so we do know that this is accelerating at 3.6. I think it's 3.63 or something like that. With 3.6 even? 3.5. 3.56, something? Okay. It wants me to find the coefficient of friction right there. I'm going to focus on the 2 kilogram mass. I'm going to do a free body diagram for the 2. What are the forces acting on it? Get the obvious one. What else? Normal force poking up. Now it gets tricky, so I'm going to go much more meticulous. Which way is mass 2 accelerating? To the right? So there has to be a force pointing that way. What force? Is it the rope? Is the rope touching mass 2? It's not tension. I thought about this, and I really wasn't quite sure. This is not an applied thing, because the net force is being caused by gravity on this 8. There's no outside off the page applied force. I know there's a force here. What is it? So I thought about this, and I said, wait a minute. What if this was made out of ice? What if the 12 was pure ice? Wouldn't it get yanked out and the 2 kilogram would just drop straight down, like when you try pulling out a magazine from another stack of magazines, if you yank it out quick? And Braden, what force is it pointing to the right then? This was my eye-opener. I went, oh. And now, who's winning? Friction. Who's losing? Trick question. No one. So my equation looked like this. Friction equals ma. I said friction equals what times what? Mu times, I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. M2G, and I should have put M2A up there. I'm looking at the mass number 2, the 2 kilogram mass. Kind of cool. The masses cancel. How would I get the mu by itself? It's going to be the acceleration from part A divided by 9.8. That's the minimum coefficient of friction. Could be bigger. You could have extra room to spare, but you need at least that much mu. You'll notice, this is why I said so easy that it's tough. A free body diagram, 2 lines, and I'm good. Far less work than many of the other questions. So easy that it's tough. Isn't that neat? Kind of cool. Today, your other question you asked about was, I think, the finding the mass one, 15. I'm going to be covering finding masses today, I think. So, pause that. Your hint is we're going to use Math 9, of all things. So the Atwood machine is a physics construct, but it's a mythical, magical, can't exist in real life physics construct. It's a pulley system as seen below, or if you look up like this. When one mass, keep them untangled, Mr. Duick. When one mass goes up, the other mass accelerates down, and vice versa, and they're attached by ropes, so their accelerations are the same, except here's where the physics breaks down. Our ropes have no mass, because otherwise this mass would be very different from this mass, because I'd have to take the changing mass into account. You need calculus. Our pulley will have no friction and no mass either, because that makes yucky math. But otherwise, there's some good physics we can do here. And I think I said to you, mass 2 makes it easier for a person or a motor to lift mass 1. The mass M2 is called a counterweight. So here's our first thought experiment. It says this. Identical masses are placed on both sides of an Atwood machine. So you need to look up, imagine this is the case, except imagine right here, no friction. Perfectly smooth, no friction. One of the masses is lifted higher. For you, it's the one on the right. If there's no friction, and I release the higher mass, what happens? A, the system remains at rest, nothing happens. B, the higher mass is going to fall down to the ground. Or C, the lower mass is going to fall, lifting up the higher mass. Hey, we get to vote! Once again, how high we hold our hand up is how sure we are of the answer. So you see the thought experiment? A, the system remains at rest. B, the higher mass falls back down to the ground because you've lifted it up. Or C, the lower mass is closer to the earth and gets tugged stronger, lifting up the higher mass. Who says, yeah. Oh, we're voting? Ready? Who says A, remains at rest? 10. Who says a higher mass falls? Who says higher mass goes higher? 5. Lyndon, where are you going? I don't know the answer. You know what? This is a job for a free body diagram. Okay. I'm going to zoom in to the right-hand diagram. And let's label our forces. What are the forces acting on this higher left-hand mass? Get the obvious one. What else? Is there a rope? Tension? Pointing which way? Up. On the right hand, is there a normal force? We're not on a surface. I think that's it on the left-hand side. On the right-hand side, what are the forces acting on this? Get the obvious one. Now, normally I call them M1 and M2, but are both masses identical? Does it say that? Then I'll use the same letter for both of them. What else? Tension. Now, some of you voted for option C, the higher mass going higher. If the higher mass is going higher, then I think you're saying that this is winning. Is that okay? I can't say MG because there's two of them. So the right hand facing downwards, MG on the right is winning. So let's decide anything that ends up pointing down and right is going to be winner plus. Anything when it gets to this side that's going to be pointing up is going to be loser minus. So let's write an equation. Who's winning? You already said MG. And we walk along the rope. This tension right here, winner or loser? Loser? Now, this tension here, you might be tempted to say, because it's pointing up, is also a loser. But if you follow it around, when it gets to this side, which way will it end up pointing? Down, which makes it a winner plus. This MG, you might be tempted to say, oh, it's pointing down, so it's a winner. But if you follow it all the way around, when it gets to this side, which way is it pointing? Up, making it a. And this is going to be M plus M times A. On the right-hand side, I can tidy up a bit. What's M plus M? What's 1M plus 1M? So this is 2MA. On the... Oh. I mean, yay, I lose tension, but suddenly I just gain some tension because something weird's happening here. What else is happening, Ange? When nothing's left behind, what's really left behind as a number? So here's what you end up with. All right. Let's get the A by itself. How? So we're going to get this. A equals 0 divided by 2M. What's 0 divided by anything? So, can we accelerate? So what's the correct answer? A, B, C, or D? Or sorry, A, B, or C? Lyndon, have I convinced? Because you weren't sure. Nice proof. So A, and where it says prove it, right there. And you'll notice no English, no letters. There's your first purely algebraic proof. Done. But what was my fallback? Hey, in forces, if you ask me a principles of physics question, most of the time it's going to involve a free body diagram, Sarah. That's going to be one of my tools. Where in projectiles, if you're asking me a question, T-table and components was probably going to be my strategy. And as the year progresses, you'll have more tools on your tool belt that you'll go with. Let's do one with numbers. It says in the diagram below, Let's assume mass 2 is 5.8. You know what? I think I'm going to write that in. And let's assume mass 1 is 2.3. Solve for the acceleration, find the tension in the cord. Okay. Well, let's do our usual, this is a job for a free body diagram, but since they gave us more than one mass and a picture, rather than doing a completely separate free body diagram, I think I'll just label what they gave me. What are the forces acting on M1? Get the obvious one. Which mg? Yep. Is there a normal force? Because there's a gap. Now, if it was still sitting on the ground, I would also have a normal force pointing up. We can handle that just fine. It gives us one more thing in our equation. Meh. What else? Tension? And I think that's it for mass 1. What are the forces acting on mass 2? Get the obvious one. M2G. What else? Tension. That's it. Who's winning? And this is where I have to ask you just to kind of use your Sesame Street imagination. It's got to be the heavier mass. There's no way the 2.3 lifts up the 5.8. I think the 5.8 pulls down the 2.3. Yes? So anything that ends up on the right pointing down is going to be winner plus. Anything that ends up on the right pointing up is going to be loser minus. So M2G. Manir, that tension, winner or loser? This tension here, winner or loser? M2G pointing down is winners. Anything that ends up pointing down is... Sorry, this tension here, winner or loser? Why'd you look at Lyndon when you said that? Wow. Wow. Jeez. Lyndon, this tension here, winner or loser? Okay. Now's your chance. This M1G, which you might at first think is a winner because it's pointing down, when you follow it, when it gets to this side, winner or loser? Did you want to look over and... Okay. What's the only other adjustment? Do we have forces from more than one mass? Well, then we better include more than one mass. Again, we get our little spa treatment. Again, honestly, if you know that the tensions will cancel and you don't feel like writing those, go ahead. I think I told you I still get a stupid childish giggle out of doing that every time, so I will. Then how to get the A by itself? It says find the acceleration. How? So you're telling me the acceleration is going to be M2G minus M1G divided by M1 plus M2? Yep. It's going to be 5.8 times 9.8 minus 2.3 times 9.8 all divided by 2.3 plus 5.8. This is worth practicing typing into your calculator, I think. 5.8 times 9.8 minus 2.3 times 9.8 divided by 2.3 plus 5.8. Double check my math, double check my typing, bracket. Come on, do it. You get 4.2345679? Boy. 2, 3, 4, 5, 6, 7, 8 would have been kind of cool. Oh, then it goes 0, 1. That's almost, anyways. 4.23. Meters per second squared. Jordan, what's B want me to find? Pick one mass. It doesn't matter which one. One will be ever so slightly easier. Because in one, the tension is the winner, which makes it easier to get by itself. So Jordan, which mass is tension the winner in? M2? You said both. Which one? Who's winning? M2. So what would the equation be for M2? Which way is M2 accelerating, up or down? This one, the heavier one, is accelerating up? I don't think so, right? A heavier mass is going to yank up the lighter mass, right? So I think M2 is winning. So I'm going to recommend we do this one. Which way is this mass accelerating? Up. So what direction is winning on the left side? Up. Which force is pointing up on the left side? M1G is pointing up on the left side? Which force is pointing up? You're way overcomplicating this. You're experiencing some tension right now. Tension is the winner here, and my equation is going to be tension minus M1G equals M1A. You could also, though, have used mass 2. Your equation there would have been M2G minus tension equals M2A. You'll get the same answer. It's just, you got to do the swappy dance, and I'm even mentally lazy sometimes. But it's such a small issue, pick whatever. Tension is going to be M1A plus M1G. Tension is going to be M1 2.3A. I'm going to write 4.23, but I'm going to use my answer button. 2.3 times 9.8. 2.3 times, answer button, plus 2.3 times 9.8. And I get a tension of 32.3. Oh, could we have used our built-in error check for acceleration in this situation? Could we have said we know for sure that it can't be bigger than 9.8? Yeah, because you've got gravity involved in this question. Okay. Tension equals 32.3 newtons. There's your Atwood machine. Now let's muck it up and say, what can I throw at you? Turns out, now that we've looked at more than one mass, with a tiny bit of cleverness, we can adapt the method that I've taught you, my winner minus loser. This whole idea of, this is a free body diagram, Newton's laws are very powerful, Mitra. We can handle situations we've never seen before. It says this: first of all, consider the following system. Which of the following is the best force diagram for mass M2? You know what? Let's do the free body diagram for mass M2. What are the forces acting on it? Get the obvious one. Does that get rid of any answers, A, B, or C? Okay. What else? Does that get rid of any answers, A, B, or C? What else? Now, here's my first question. Is that going to appear on mass 2? Is it touching mass 2? Then it's not going to appear on mass 2. Okay. What direction is mass 2 accelerating? What does Newton's first law then tell me must be the case? This is the tricycle question all over again. Which way are we accelerating? To the... So what does that mean? Has to be a force pointed that way. No friction. Let's draw the free body diagram on mass 1. Get the obvious one. M1G, normal force number 1. F applied. Pardon me? A little normal force. Let's come back to this. Let's do one with numbers. So it says this. Find the acceleration of the system and find the contact force between the two blocks. I guess the contact force is where they're touching? Oh. Are they pushing against each other? Newton's third. Forces will come in. Ah, that helps. Oh. Mass 1, mass 2. Are they pushing against each other? Well, then forces will come in. So M1 pushes against M2. That's that bad boy right there. M2 is going to push against mass 1. That's that bad boy. Sorry, that's that bad boy right there, not call it mass 1. You know what? I think A is correct because nothing else will let you accelerate to the right. The real question is, how do I know B is wrong? What is B hoping that you'll do? Take applied and have it go all the way through everything. The rule is, look, if you're not touching, there's no force there. Okay? Explain your answer. We kind of just have, but let's solve example 4. This will help. So, what are the forces acting on the 6 kilogram mass? Get the obvious one. And since there's more than one mass, I'll call that M1G. What else? Normal force, and I'll call it normal force number 1 to go with mass number 1. There's definitely F applied, but I'll call it F applied number 1 to go with mass number 1 because I scooched over and I saw on the right there seems to be another force coming from off the page too. What else? Is the 6 kilogram mass pushing against the 8.25? Then what's the 8.25 doing? There is one more force here, and this is going to be F contact. F contact. There's probably a fancy schmancy name for it, but that works. What are the forces acting on the 8.25? Get the obvious one. Normal force number 2, F applied number 2, and we're going to have F contact. We're going to, yep. We could call it a normal force. The only problem is I'd get confused. But it's if you push against that surface pushes back against you. And if we're going to define what a surface causes as a normal force, then yes. Yep. We're going to use the same strategy we did to find tension. We're going to look at the acceleration of the whole system. Write an equation for that. Find A. And then find specifics. Which way must this be accelerating? Why to the right, not to the left? 42.5 is way bigger than the 6.75. No matter what's going on in the middle. Okay, so anything that ends up pointing to the right is going to be winner plus. Anything that ends up pointing to the left is going to be loser minus. Who's winning? M1 is not even along our frame of forces here. F applied 1? And now we're going to walk along the imaginary rope. It's not there, but I can kind of imagine it there. What else? There's an F contact, winner or loser. I keep walking. I ignore M1G and F normal force 1. They're not in my direction. There's a plus F contact. And then F applied 2, winner or loser. You did it again. You said loser and you... Wow! Boy. What's it going to equal? M1 plus M2, or if you want to use something that works everywhere, M all. A. Much like the tensions, what happens to the contact forces? That's good, because I don't know. So, if I hear you folks, you're telling me A is going to be the first applied, take away the second applied, divided by both masses added together. Okay. 42.5 take away 6.75 divided by 6 plus 8.25. What are we accelerating at? $2.5081, that there? Okay, I'll go 2.51, but I'll keep this on my calculator. Now, part B says find the contact force. Doesn't matter which mass I use, but I'm going to use an individual mass equation. If I was clever, I'd try and let the contact force be pointing in the winning direction. Jordan, my friend, what direction is the winning direction here? To the? So which mass has the contact force pointing to the right? Which mass has the contact force pointing to the right? What's the equation for the second mass? We have this. Contact. Oh, and I guess there's a minus. Minus what? Applied 2. That equals M2A. So the contact force is going to be, we do the swappy dance? No, we just plus it over. Never mind. No need for a swappy dance. It's going to be M2A plus F applied number 2. What was M2? 8.25? Thank you for all helping me. 8.25. A was 2.51 plus, and then F applied was 6.75. And no dividing by. It's already going to be by itself. That works great. 8.25 times my answer button plus 6.75. The contact force between these two, 27.4. So this method of a good free body diagram, Sarah, and writing an equation on everything, and then once you know the acceleration of everything, going in targeting individual, works. It's very powerful. We can handle stuff probably that we don't know what we can handle. Next page. A couple more, we're done. Cool. A curling rock. Rock number 1 is traveling east across a sheet of frictionless ice, so we're looking down at it from the top. It bumps another rock and it experiences a force that acts briefly to the north. After the collision, what will the path be of the rock after the bump? Answer: A, B, C, or D? Once again, we get to vote. Once again, how high you hold your hand up is how sure you are of the answer. A, B, C, or D. So the second rock, they collide. Wham, they collide. After the collision, will the first rock be traveling path A, path B, path C, or path D? Who says A? Get pushed straight north. A. Who says B? It's going to keep going in a straight line at a steady speed. Who says C? It's going to travel in a circle. Who says D? Convince me. Why must A be wrong? Yeah. Okay. Nothing canceled out east. So A must be wrong. Let me just shrink this down a bit so I can get this all on one page. Why must B be wrong? A force was applied north, so it must accelerate north, at least for a split second. Why must C be wrong? Why wouldn't it slowly go in a corner like that, in a curve like that? What's the acceleration taking the form of in part C? Not a magnitude change, but a what? Direction change, which is still a change in velocity, which is still an acceleration. So C, direction change means there is still a force acting. So we've shown that A and B and C must be wrong. D is all that's left. You might be able to just go with the argument. Probably you could answer, Kevin, components and things and do a lovely proof to prove that D must be right. But sometimes if I can just see that the other three are wrong, it's an easier way to go about it. All right. Next thought experiment. Suppose we take a water bottle and we drill it full of many small holes so that it leaks when it's filled up. If the bottle is filled up and then dropped, what happens as it falls? A, the water stops leaking out. B, the water leaks out at the same rate. C, the water leaks out at a slower rate. Or D, the water leaks out faster. Mr. Duck? What, Caleb? Can we try that? Sure we can. Correct answer was, sorry? Okay. Why? Why? You know what this is a job for? I think if we do a free body diagram on the bottle, so here's the bottle, or the bucket, whatever you want to call it, and over here we're going to do a free body diagram on the water. What are the forces acting on the bottle? Get the obvious one. What else? A minor amount of air resistance, but I think it was negligible. What else? Anything else? Huh. What are the forces acting on the water? Get the obvious one. What else? Well, the normal force would be only if the bottle was not in free fall. Because if you're in an elevator in free fall, what's your normal force? 0. Was the water in the equivalent of an elevator in free fall? So I'm going to say 0. I'm going to argue same acceleration, because in both of those, A is going to be 9.8, because that's the only force acting on you. And they both started with the same initial velocity. Whether I threw it up or dropped it, they still had the same VI, had the same A. Is there any way that one can get ahead of the other? Okay. Same A, same VI. So, same distance everywhere. They'll stay together. Is that all right for my explanation? I could probably write something flowery and longer than that, but that gets it across. Last one. I like example 7. I like example 7. I like example 7. Example 7 is a nice question. Example 7, Manir, is also an answer to how you would handle number 15 from last day. Because what am I asking you to find in example 7? A missing mass. This is physics 12. Up until now, everything I've done was physics 11. All right. It says if mass 2 is 8.4 kilograms and accelerating downwards at 3.5, What's the mass of mass 1? Well, it's still a job for a free body diagram. What are the forces acting on mass 1? Get the obvious one. What else? Tension. What are the forces acting on mass 2? Get the obvious one. What else? Tension. Do I know both masses, Matt? So my normal approach of writing an equation for everything, since that has both masses in it, instead, we're going to reverse the procedure. We'll write an equation for one mass. The mass that we know. Which is the mass that we know? M2. Okay? Which way is M2 accelerating? This is why I had to tell you that, because you need to know who's winning. So let's make a little note here. A is that way. Draw a little arrow on it. So writing an equation for M2, who's winning? Who's losing? What does that equal? What can I find here? I can find tension. Now, why is that nice? Because the tension for mass 2 is the same as the tension for mass, which might let me then figure out how big mass 1 has to be. See our approach? So we'll do the little swappy dance. We'll get tension equals M2G minus M2A. Tension is going to be 8.4 times 9.8, take away 8.4 times 3.5. So my strategy is this, Ange. Give me both masses. I'll use both masses to find total acceleration. Then I'll go look at individual masses. Missing a mass? Start with the individual mass that you know. Use that to find other individual forces, and then go look at the individual mass that you don't know. Tension, what'd you get? 8.4 times 9.8 minus 8.4 times 3.5. 52.92, and since this is not my final answer and I'm going to use this, I'll carry all the extra sig figs. Now, Sarah, we're going to write an equation for mass 1. Which way is mass 1 accelerating if mass 2 is accelerating down? Up. So who's winning? Yes, Jordan, tension is winning. So what's my equation going to be for mass 1? Tension minus M1G equals M1A. What are we trying to find here? Mass 1. How many M1s do I have in this equation? 2. How many would I prefer? You know what? Let's get them all to the same side. I'll plus the M1G over. Sarah, how many M1s do I have? How many would I prefer? You know, it'd be really cool. It'd be really cool if it was a grade 9 mathematical operation that I could pull out of my back pocket from Math 9 that would somehow change this from 2 M's to 1 M. There is, and for a candy, if anyone can point it out. Nate, what did you call that? The math F word, not the F word you're thinking of.
Factoring.
This is greatest common factor, GCF. Is there an M1 in everything on the right?
Yes.
Then I can write this as Sarah, why is that so nice? How many M1s do I have now? How many would I prefer? Oh! Cool. Final question, Munir. How to get the M1 by itself? The bracket. Oh, wow. Math 9! Really? Mr. Dewick, you said this was Physics 12. You should have said this was Physics 9. 9! Or is that a...
Yes. Saying no. Yes.
M1 ends up being tension over A plus G. You can't just memorize that equation. Depending on whether your mass is accelerating up or down, winning or losing, sometimes it will be tension over G minus A, sometimes it will be tension over G plus A. Do the free body diagram and walk through it. So it's going to be 52.92 divided by, what was A? I've scrolled, 3.5? How many kilograms must mass 1 be? Divided by bracket 3.5 plus 9.8. You get 3.98? As an aside, I wrote here, you are now technically capable of doing any question from that big ultimate review that doesn't have angles or a rep. Okay? I gave it to you with lesson 1. Go check, you have it. Okay? The ultimate vector dynamics review. No, I called it the ultimate vector dynamics review. Angels, what's your homework? Number 1 we already did. We did the experiment. Back here. Hello? So what happens when the bottle is rising? Same reason, because same VI, same A. The distances between the two of them can't change. Okay. Find the acceleration of these systems. Number 2 is fair game. In number 2, the second one, you could either let M be a nice number, like 5, which would make the left-hand mass 15 and the right-hand mass 5. Or if you want to, try doing it algebraically, and you'll find towards the end suddenly the capital M's all cancel, and you get a numerical answer. Either or is fine. 3 is good. Eight is good. Number 9, if you look up, here's the hint for number 9. So number 9 wants you to figure out how high mass 1 will reach. I'm going to tell you what's going to happen. This is mass 1. It's on, never mind, mass 1 is on your right, so let me reverse things. If this is mass 1, here's what I think is going to happen. This is what you have to take into account to get the correct answer of 8.17 meters. When it hits the ground, I'm going to do it on the chair here. When it hits the ground, watch this string very closely. What do you notice in the string for a split? There's going to be a brief moment of free fall while it's still on its way up. And so the maximum height is at the very, very top when its final velocity is what? 0. How fast is its initial velocity? That you'll have to figure it out by finding the acceleration while it's in free fall. You can figure all of that out. It's a tricky question, but it's actually all physics 11. Nothing new there. Is Physics 11. If you wanted to say, oh, what were some of the old scholarship ones? This was from an old scholarship exam. But absolutely number 10 is not scholarship. I'm going to give you a missing mass question on your Physics 12 test. It's either going to be an Atwood machine completely like this, or like the homework from last day, number 15, where one mass was hanging over a cliff and one mass was on a flat surface.
Which ones are we not supposed to do?
The ones that I circled are the ones you are supposed to do. So 10, 9, 8, 3,
Oh, okay.
2.
Yeah.
We already did number 1. Okay, so I let you skip 4, 5, I don't know. And if you're wanting to, we're getting close to the end of the unit. I have technically 2 more lessons? 3 more lessons. So your test, I'm not going to be able to, I don't think, fit your test in before the Remembrance Day long weekend. It'll probably be shortly thereafter. I'd like to get it in before then, because I think, you'd rather have no homework for the weekend and do it before then, but we'll see. Physics 12 really begins next class. We're finally going to say, what if you're on an angle? So there's about 8 minutes left. Get a chunk of the homework done. You can probably get most of it done just in this short chunk. I gave you all the nasties as practice. I skipped some of the easier ones aside from question 2.